Hello everyone. I'm Gitanjali Jaina. I'm a research scholar from IIT Delhi and the PMR for this course, which is Physics of Linear and Nonlinear Optical Waveguide. So as I said before, in each live session, we'll go through the concept related to, we will go through the some of the numerical problems that is related to the concept that has been taught in this week, which is week 9. And in this week, we primarily we saw what is fiber Bragg rating and what is the condition for a fiber Bragg grating to have a strong reflection at specific wavelength, and what are the value for reflectivity at different length, and what is the coupling coefficient between two different modes that is propagating along the fiber Bragg rating. So, this live session, I will go through the some of the numerical problems that is related to fiber Bragg rating. And okay, so the fiber Bragg rating, it can be of two types. One is it can be periodic Bragg rating or aperiodic Bragg rating. So we'll see both of the problems. It's not like I will primarily focus on periodic Bragg rating. So we'll see chopped fiber Bragg rating, which is a typically example of aperiodic Bragg rating. So let us go through the first question. This covers the concept that we have seen before, as well as the concept that is related to the week 9. So the question is, consider a step index fiber with a refractive index. Let me uh, write the parameter that is already given to us. So N2 is already given, it is 1.45, and the core radius, it is also given 3 micrometer. In the numerical aperture of a step index fiber, it is given 0.1. So this is for the step index fiber. So the first part of the question asks, at 550 nanometer, will the fiber support LP01 and LP11 mode, right? So this, if you recall, this we have already seen before, few lectures back. We have already seen what are the condition for a step index fiber to support certain modes. So if we recall the graphs, so to support the modes, we have to see what is the B versus B curve. Okay, so this is only for you to recall what is the concept that we have seen before. So if you recall, so the BV curve, this is B and this is V. And the graph is like, this is for LP01 mode, the variation of B with respect to the wave number. Then we have LP11 mode, then the higher order mode. So this is for LP01, this is for LP11, this is for LP21, and this is for LP02. And the cutoff wavelength for LP11 is 2.4048, and LP21 and as well as LP02. It is these two have the same cutoff value, which is 3.8317, right? And LP01 mode, if you recall this from the graph also, you can see the LP01 mode. It doesn't have any cutoff. So this is one of the fundamental concept. It doesn't have any cutoff wavelength. So that means this mode will always be guided inside the step index fiber. And how to find out whether this supports LP11 mode? So we have to see what are the cutoff condition for LP11 because LP01 is always guided, so there is no need to worry about that. For LP11, so uh, this will be guided only when the V parameter lies between 2.4048 okay, minute. I'm not audible even now. So Lena, can you let me know whether I'm audible? I think from my side the mic is working. Um, can you check yours? Okay, it's fine now. Okay. So, okay, let me give you a brief what I've said before also. So these are already given to us, like the step index fiber, this parameter is already given. In the question, the first part of the question asks whether the given step index fiber, whether it will support LP01 and LP11 mode or not. So for that, we have to look at the BV curve, which is the plot between B and V. So if you see the LP01 mode, it is always guided inside the fiber. It doesn't have any cutoff wavelength. Okay. So at least one mode is always guided inside the step index fiber. For LP11, so the V parameter it should lie between this region 2.4048 to 3.8317. It should lie between these values. So now our main work is to find out what is the V value. Sorry, to find out what is the cutoff wavelength for that, for LP11. So this V is 2 pi A square root N1 square minus N2 square, 3.8317. So square root N1 square minus N2 square, it is nothing but the numerical aperture of the fiber. If we consider that the surrounding medium is air, so this is numerical aperture. So please go through the concept again and again so that you don't make any mistake in between the step. Okay, because sometimes what happens, you read it is a step index fiber, but you usually take any other cutoff condition. So please be mindful while reading the question. So okay, so core radius it is already given. It is 3 micrometer and numerical aperture it's already given. It is 0.1. Okay, so just make some rearrangement so that you can get what is the cutoff wavelength. So this is 2.4048. This value will get 1.884 and this is lambda. This is 3.8317. So now if we take the inverse, this will be 1.884 over 2.4048 and the sign will change and this will give 1.884, 3.8317. So this will give 0.784 micrometer and this will be 0.492 micrometer. So let us see what is the wavelength given. It is 550 nanometer, which is 0.55 micrometer. So this lies in the range, right? So that means now the fiber, the step index fiber will support LP01 as well as LP11 mode. So this is all related to what we have seen before. Now next, what we have in the B part, it's given if a fiber Bragg grating is to be made to strongly reflect the LP01 mode, then what should be the spatial grating period at 550 nanometer, given that the effective index for LP01 mode is 1.4517. So if you recall the lecture, it's a direct implementation of the Bragg wavelength condition. Okay. So let us see for the B part. We have for what is the condition for strong reflection? So strong reflection means the forward propagating mode. It is strongly coupled. It should be strongly coupled with the backward propagating mode. So for that, what we need, the phase mismatch parameter, which if you recall the lecture, it is gamma, right? So gamma, it is given by beta 1 minus beta 2 minus k. It should be 0. And when beta 1 equal to beta 2, we have this is 2 beta, which should be equal to kappa. And this, if you solve it, like take beta is k0 and effective, and k is 2 pi over the spatial period. So this will give spatial period is lambda b, which is Bragg wavelength, over 2 n effective. So this means lambda b is already given in the question. It is 0.55 and 2 into 1.4517. This is also given in the question. So this will give approximately 0.19 micrometer. That means the spatial period should be in the order of 0.2 micrometer. Now, if you look at the transmission graph for this, so what will be the transmission graph is like? If it is a T versus lambda, so only the wavelength corresponding to 0.55 will be reflected. So transmission is 0, and other wavelength, it is transmitted through the fiber Bragg grating. And this type of behavior, if you see the graph, we have maximum transmission for all the other wavelength without any loss. But at this wavelength only, at the desired wavelength, the transmission is almost 0. So that means this we term is that the fiber Bragg grating, it acts like a notch filter. So this is how the notch filter works. Like for notch filter, only at a desired wavelength the transmission would be 0, and at all other wavelength the transmission won't be affected. Okay, so that means we can use the fiber Bragg grating as a notch filter. So this is for the application purpose. Now let us see what is question 2. So question 2, it says, consider a fiber Bragg rating with the following parameters. Effective refractive index, and effective is given, which is 1.45, and the refractive index modulation is also given. This is delta n is 5 into 10 to the power minus 5. Grating period is also given, gamma, sorry, grating period 600 nanometer, and the length of the grating is 10 millimeter. And the question says, under the pure phase matching condition, that is gamma is 0, the Bragg reflectivity of the fiber is, so what is the approximate value of Bragg reflectivity under pure phase matching condition? So if you recall the lecture, so reflectivity, it is given by R is tan hyperbolic square kappa L, where kappa is the coupling coefficient of the fiber Bragg rating. So kappa is not given, so we need to find out what is kappa first. Let us see. So before that, what we can do? So let us see what is tan hyperbolic kappa L. So this is square root R. No. So let us first calculate what is lambda B. So lambda B for the pure phase matching condition, this is 2 N effective multiplied by the grating period. N effective is given, it is 1.45, and okay, so grating period is 600 nanometer. So this will be 1740 nanometer. And if we recall the, okay, in the question it is delta n is given, lambda v we already have calculated, and the n effective is also given. So that means if you recall the lecture, the one of the expression for coupling coefficient, it is given by pi delta n over lambda b. We'll see a general formulation for this coupling coefficient, but for now we can take the expression as pi delta n by lambda b. So delta n is already given, 5 into 10 to the minus 5, and lambda b, it is 1740 nanometer. So this will give a value 90.2 meter inverse. So we know what is kappa now. So that means we can easily calculate what is the value for Bragg reflectivity. So Bragg reflectivity, kappa is already given. We have calculated it. So R is tan hyperbolic square kappa L. So kappa L is, this is 90.2 meter inverse. L is given 10 millimeter. So then 10 to the minus 2 meter. So this is 0.902. So how to find tan hyperbolic square kappa L? So you can use tan hyperbolic x is e to power x plus e to power minus x over e to power x. So this is the numerator part is minus, and we have e to the power x, e to the power minus x. So you can use this. Here x is kappa L, which value is 0.902. So that means you just need to find out e to the power 0.902 minus e to the power minus 0.902 and e to the power 0.902 plus e to the power minus 902. So just use this and square the value so that you can get the square of tan hyperbolic x. So if you calculate it, it will come around 0.514. Okay. So at this length, the reflectivity will be 0.514. Let us see what is question number 3. Let's go through the question once. So a fiber Bragg rating is given, which is the parameter one is N effective. It is 1.46. And the refractive index modulation is also given. It is 8 into 10 to the minus 5. Other value is reflectivity is given, which is 0.75. And the length of the grating is 8 mm. So the question says, under pure phase matching condition, what is the grating period of the fiber Bragg grating? So what is grating period now? So when you are given the reflectivity delta and ineffective and L. So this is also easy to solve. So if you recall, R is tan hyperbolic square kappa L. So which is given, it is given 0.75. So that means tan hyperbolic kappa L is square root R, which is square root 0.75. So we need to find out what is kappa L first. So which you can find it by taking the inverse of tan hyperbolic function. But the other way is you can use the expression of tan hyperbolic, which is e to power x minus e to power minus x over e to power x plus e to power minus x, which is square root 0.75. To solve it, you need to make some algebraic manipulation. So this is, so if you add e to a minus x and subtract e to a minus x, so this won't change the result. Square root 0.75. Now this by this will give 1. And there is 2 e to power minus x divided by e to power x plus e to power minus x. So now we can rearrange it again. So this is e to the x plus e to the minus x. This will be 1 minus square root 0.75. So to get e to the minus x, we need to eliminate the exponentials. Okay. So for that, let us take inverse. So this will give 1 by 1 minus square root 0.75. So we have now, so if you divide it 1 by 1, so this will give half e to the minus 2x plus 2x plus 1, which is 1 by 1 minus square root 0.75. So this will again give 2 by 1 minus square root 0.75. So that means e to the 2x is, it will give 1 plus square root 0.75 over 1 minus square root 0.75. Now it's easy to eliminate the exponential by taking a logarithm. So ln e to the 2x will give 2x. This is ln 1 plus square root 0.75 1 minus square root 0.75. So x is nothing but kappa L, right? This is, so if you take L to the right hand side, this will be 1 by 2L. ln 1 plus square root 0.75 by 1 minus square root 0.75. So for a general expression, what we have, kappa, you can calculate the kappa if the length of the fiber grating is given and taking the logarithm of 1 plus tan hyperbolic kappa L over 1 minus tan hyperbolic kappa L. So for our case, let us see. So tan hyperbolic kappa L is square root 0.75 and L is given, it is 8 mm. So that means kappa is now 10 to the 3, 2 into 8, then 1 plus square root 0.75, 1 minus square root 0.75. So this will be the order of 164.6 meter inverse. So we know kappa now. And if you recall, so we have seen before also in the previous question. So kappa, you can write it as pi delta n over lambda p. And lambda p for the phase matching condition, it is 2 an effective grating period, right? So that means the grating period that we need to find out, it can be expressed as pi delta n over 2 an effective kappa. So this, all the parameters we already know. Some of the, like the kappa we have derived, but all other parameter is given. So delta n is given 8 into 10 to the minus 5. 2 n effective is, it's already given 1.46. I think it was 1.46. Okay. 1.46 and this is 8 mm. Okay, so kappa is 164.6. So this will give a value of 523 nanometer. Okay, so this is the answer. So let us see what is question number 4. So please go through the question once. I think my handwriting is visible, right? Okay, so go through the question once. So the grating is like we have a fiber Bragg grating, which is so the some of the reason have diffractive index n plus delta n, and some of the reason has refractive index n minus delta n. So this is the fiber grating which is given to us. In the so it is given the reflection spectrum of a fiber Bragg grating of length 2 mm. Let me take a different color. 2 mm sources are peak of bandwidth 2 nanometers centered at 1.5 micrometer. So that means this is the Bragg wavelength. And whenever we have a peak, it's not like it says our peak. So we'll have a spreading around this Bragg wavelength. So that is why in the question it is given the bandwidth of this reflection spectrum around 1.5 is 2 nanometer. So we have delta lambda. It is 2 nanometer. And other thing is given that the propagating mode inside the fiber has a effective index 1.46. 1.46. So in the first part, it says to calculate what is the period of the grating, which is easy to solve, right? Because we just need to use the formula here, lambda b, which is 2 n effective and the period, grating period. So that means the grating period will be lambda b over 2 n effective. Lambda b is given, it is 1.5 micrometer, and this is 2.2 into 1.46, which will give a value of 0.5136 micrometer. So the first part was easy. For the second part, it asks us to find out what is the peak reflectivity of the fiber Bragg grating. So from the formula of the reflection spectrum, R will be tan hyperbolic square kappa L. This is the reflectivity when we have the pure phase matching condition. That is when we have gamma is 0. So L is L is already given to us, which is 2 millimeter, but we don't know what is the value of kappa for this. fiber Bragg rating. And delta n value is also not known to us. So that means we can't use this formula pi delta n by lambda b. So delta n is it's known to us. But is given to us is delta lambda, which is the bandwidth of the reflection spectrum. So for delta lambda, so I will directly write the expression for delta lambda. So when we have pure phase matching condition, you can write delta lambda as lambda b square n effective L square root 1 plus kappa L by pi square. So you can use this when we know the if you know the what is delta lambda, if the delta lambda is already given to us. So now the question seems easy because delta lambda is given, it is 2 nanometer, and lambda b it is given 1.5 micrometer, and n effective it's given 1.46, and L is given, which is I think 2 mm. So just put the parameters in the expression here. So we know this, all these parameter, only the k is not known, that we can find out. So if you use this, we have 2 into 10 to the power minus 9 lambda b square, which is 1.5 into a minus 6 square, 1.46, L is 2 mm, square root 1 plus kappa is it's not known, kappa L by pi square. So if you take this expression here, we'll get, so let me directly write. So if you take this value here to the left hand side and take the square of both sides, we'll get 1 plus kappa L by pi whole square, which is equal to 6.7369. So that means now kappa L by pi whole square is 5.7369. So kappa L is now pi square root 5.7369. So this will come around 7.5247. Okay. So now we know kappa L, so that means we can find out what is reflectivity, which is tan hyperbolic square kappa L. This you can write it as e to the power kappa L minus e to the power minus kappa L e to the power kappa L plus e to the power minus kappa L square. So it was 7.5247 minus it was 7.5247. Same expression with a plus sign. So this value will come around 0.99. Okay. So only thing to remember is this expression. The third part is it is asking about what is the difference between the highest and lowest value of refractive index in the fiber core. So if you see the figure, the maximum refractive index is n plus delta n, and the minimum refractive index is n minus delta n. So that means the difference in refractive index. So let us take, let's say this difference will be 2 times delta n. So we need to find out delta n, right? And how you can calculate delta n now? So n max is because we already know kappa now, which is the coupling coefficient. Now, if you equate it to the expression that we have already known before, which is pi delta n over lambda b. Kappa is already know. We already know what is the value of kappa. So delta n will be kappa lambda b over pi. So can you please calculate it and let me know the answer? So given kappa L is that we have calculated before, it is 7.5247 and L is given, it is 2 mm. Then what will be delta N now? Please calculate it. 3.86 mm. I think you got it. So it's not correct, I think. Because lambda b, okay, I have not mentioned what is lambda b. So lambda b is it's given in the question 1.5 micrometer. This is delta n. So have you used lambda b as 1.5 micrometer? Okay, then don't be like that because kappa, I think it will come. Okay. So let me see. So delta n is, so we know the value of kappa n. So one thing that we can do here is multiply L in both numerator and denominator. So kappa L lambda b pi n. So kappa L is known, it is 7.5247 5247 into lambda b is 1.5 into minus 6 3.14. L is 2 mm. So let me see. This will come around. The order of fluids is, yes, the order was same. It will come around millimeter range, but this is 1.7964 or 73. Sorry, 73 millimeter. So now we have only, so difference will be 2 times delta n, which is 2 times 1.7973. This will come around 3.5928 millimeter or 3.6 millimeter. Okay, let us see what is question number 5. Go through the question once. So this question number 5 is it's related to what we've seen in question number 4. The question says consider a fiber Bragg rating at 800 nanometer that should have a reflectivity of 90% with a length of 25 millimeter. Then find out the value of delta n and delta lambda, which is the bandwidth, if it is given that n effective is 1.46 at 800 nanometer. So we need to find out delta n and delta lambda. So delta n is related to kappa. So if we can calculate what is kappa, then we can find out what is delta n. From that, also using the expression for delta lambda, we can find out what is the value for the bandwidth. So let us see what we have. So lambda b is given 800 nanometer, which is 0.8 micrometer. And reflectivity is given, which is 0.9. L is given 25 mm. And effective is 1.46. Okay. So R is the expression for R is tan hyperbolic square kappa L, which is 0.9. So tan hyperbolic kappa L should be square root 0.9. So to find out kappa, we've seen before in the previous question that we can write kappa as 1 by 2L ln 1 plus tan hyperbolic kappa L, which is square root 0.9, and 1 minus tan hyperbolic kappa L, which is square root 9. And L is given, it is 25 mm. So this will be 1 by 225 into 3 ln 1 plus square root 0.9, 1 minus square root 0.9. And this will come around 0.073 millimeter inwards. So now we know kappa, that means we can equate it to pi delta n over lambda b, which is 0.073 millimeter inverse, which is 10 to minus 3. So delta n will be 0.073 10 to minus 3. Lambda b, it is given 800, which is 0.8 micrometer over pi, which is 3.14. So this will give 0.0186 to 10 to minus 3. So always remember what is the expression for kappa in terms of tan hyperbolic. So remember the simplified expression, because you can't calculate what is the tan hyperbolic directly. Okay, so delta lambda, it's we have seen before, it is lambda b square n effective L square root 1 plus kappa L by pi square. So lambda b is given 0.8 micrometer square. N effective is given 1.46 and L is 25 mm. Square root 1 plus kappa L. So kappa L will come around. So if you multiply kappa with L, this will be 1.825. So solve it, you will get this will be 0.02 nanometer. So let us see question number 6. Please go through the question once. Even in the calculator also, you can't find tan hyperbolic function. It's not there, I think. Exam will have access to scientific calculator in exam, so you can directly get the value of time. I don't think in scientific calculator you can directly calculate an hyperbolic. It's not there. Okay. So if you can calculate directly by calculator, scientific calculator, then you can directly use that. Exam, calculator is allowed thing. Okay, if it is there, then you can easily use calculator. No need to use this expression of 1 by 2 ln this expression. So I think hyperbolic function, okay, hyperbolic function is there. So you can directly, so no need to remember this. Okay, let us see what is question number 6 now. So the question says, uh, say, bit long question, but so let me read out the question for you. Consider two contradirectional coupling between two LP01 modes in a fiber Bragg rating with core radius A is 6 micrometer. The modal fields can be approximated by a Gaussian, which is psi is 2 by omega 0, square root omega mu 0. So this is the expression for the propagating field inside the fiber. And the periodic refractive index perturbation, the expression is given. So inside the core, it is non-zero, and outside the core, it is 0. Then what is the value of coupling coefficient? If it is given that the spot size is 5 micrometer. So how you can approach this one? So just use the expression of kappa. So another expression of kappa is, it is K0 square sigma over 4 beta 1. And if you, so this you can also write it as K0 square delta n square xy by 4 beta 1. So this means, so we can we can do a algebraic manipulation to get our answer. So 4 beta 1, let's say so we can always multiply 1. 1 is always there. And for a slowly varying approximation, we can use 1 as beta 1 by 2 omega mu 0 integration delta n square xy psi 1 star psi 1 dx dy. So this is one for a slowly varying approximation. So we can use this term inside this. So kappa will be A0 square 4 beta 1. This is beta 1 by 2 omega mu 0 double integration delta n square xy psi 1 star psi dx dy. So beta 1 will cancel. And to simplify it further, you can take so K0, if you remember, it's say omega yc, right? Or omega square root mu naught epsilon. So that means K0 square is omega square mu 0 epsilon. So if you use it here, kappa will be K0 square, that means omega square mu 0 epsilon 0 8 omega mu 0 double integration delta square xy psi 1 star psi dx dy. So this is psi 1 psi 1. If they are equal, you can take both area, both as a psi 1 psi 1. If they are different, then you can take psi 1 star psi 2. So 1 omega will cancel. This will cancel. This will be omega epsilon naught 8 integration delta n square xy psi 1 star psi 1 dx dy. So let us see what is given to us. What is the information for psi 1 and delta n square? So delta n square it is given. It is delta n square 1 minus r square x square inside the core, or it is 0. So that means delta n square is non-zero in the range from 0 to a. So the limit of integration for the position is 0 to a. Okay. And in a cylindrical, so it is the integration is in terms of dx dy. So we need to convert it to cylindrical coordinate system. So in cylindrical coordinate, you can express it as a r dr d phi. Okay. So kappa is, and psi 1 is also given. It is 2 by omega 0 square root omega mu 0 pi beta e to r minus r square omega 0 square. So we have omega epsilon naught by 8 delta n square. So I have taken this one out in the integration, and this is 1 minus r square by a square psi 1 star psi 1. So this will give 2 by omega 0 square omega mu 0 by pi beta e to r minus 2 r square by omega 0 square r dr d phi. And the limit for r is, as I said before, it is from 0 to a. And for phi, it will be 0 to 2 pi for a complete circle. Okay. So now we have, so let us separate the constant term. So this is 8 delta n square. So d phi will give a 2 pi term. And we have this term. 2 by omega 0 square omega mu 0 by pi beta integration. So now it will be a single integration for r 1 minus r square by a square r dr e to r minus 2r square by omega 0 square. So let us take this as a constant and let us calculate what is the value for this one. So we have 0 to a 1 minus r square a square r e to r minus 2 r square by a omega 0 square dr. So this is, so we can separate it out. R e to r minus 2r square omega 0 square dr minus r cube is omega 0 square. So we need to find out what is the integration for this. So I'm just writing the answer. So you can use integration by parts as well as other integration techniques. This will give omega 0 square by 4, 1 minus e to the minus 2a square by omega 0 square. Let us say this value is I1. So we have omega 0 square by 4 I1. Okay. So in the other part, it involves R cubed. RQ a square, it were minus 2 r square, omega 0 square, dr. This will give omega 0 4, 8a square, 1 minus 1 plus 2a square, omega 0 square, it were minus 2a square, omega 0 square. Let us take this is I2. So let us calculate what are the values for I1, I2 because this part is known to us. 2a square by omega 0 square. So A is given, it is 6 and the spot size it is given 5. So this will come around 2.88. And so that means it were minus 2a square by omega 0 square. It will be around 0.056. So this we can use this. Other is let us calculate what is 1 minus e to the minus 2.88, which is this is I1. So I1 will be, this will come around 0.944. And for I2, we have 1 minus 1 plus 2.88 e to the minus 2.88, which will come around 0.78. So we know I1, I2 now. That means we have M1, it is omega 0 square by 4, 0.944. M2, it is omega 0 4, 8a square, 0.782. So let us put these values in the integration that we have seen. Okay, this integration. So we have kappa, which is omega epsilon naught by 8 delta n square 2 pi 4 by omega 0 square omega mu 0 pi beta m1 minus m2. So we have omega epsilon by 8 delta n square 2 pi 4 by omega 0 square omega mu 0 by I beta. So M1, M2, you can see this we can take a common. So we can take out omega 0 square by 4 outside. What we have now is only 0.944 and omega 0 by a square multiplied by 0.782. Omega 0 square will cancel. Pi will cancel. 4 will cancel. And 2 will cancel with 4. So we have now is omega square mu naught epsilon naught delta n square of 4 beta. And this is 0.944 minus omega 0 by a is 5 by 6 square 0.782. So this, if you recall, this is nothing but k0 square, right? So this is k0 square delta n square 4 beta, and this will come around 0.944 minus 0.543. So just check whether you are getting this or not. Now to simplify it further, what we can do, delta n square, which is nothing but sigma. Sigma, if you recall, it is 2 n1 delta n, right? And beta, you can write it as k0 n effective. So k0 n effective multiplied by 0.401. So k0 will cancel. And you can take n1 is n effective. So you can do a approximation. Then it will also cancel. 2 will cancel. 4 will cancel. So what we have k0 delta n over 2 n effective. Multiplied by 0.401. And k0 is 2 pi over lambda 0. This is 2 pi lambda 0. So this will give pi delta n over lambda 0 multiplied by 0.401. Okay. So this value we have already seen before. So we have taken kappa as, so if you recall in question number 1 and 2, we have taken k as pi delta n over. Okay. So N1 is, it's like you do a approximation. It's like N effective. It's lie between N1 to N2, right? For a guided mode, it should lie between N1 and N2. And the value of N1 and N2, these are close to each other. It's like if one is, let's say it is 1.46, then other is around 1.45. So it's like an approximation that I have done is that N1 you can write it as N effective. So we can take one such approximation if you want. So is it clear? If not, you can write N1 also. It's not a problem, but N1 and N effective, these are close to each other. So that is why I have cancelled it out. So that means if you recall question number 1, we have taken kappa is only pi delta n over lambda 0. But the actual expression for the coupling coefficient is, this is the actual expression, which is pi delta n I over lambda 0. So I here is a transverse overlap integral of the model Hill distribution with region where grating is formed. So this is the integration that we need to consider. Okay. And in the early, so this value will be 1. So when we have a plane wave interaction in a medium, then we can take I1, so we will see that I will come around 1. So that is why in the question number 1 and 2, I think we have taken only kappa is pi delta n over lambda b. Because in that case, by the couple mode theory, if you recall, we express the psi as az e to power minus or plus beta 1 z, sorry, not z, okay, z only, beta 1 z minus omega t. So we express in terms of the plane waves. So for plane waves, we can take I equal to 1. But in denominator, we use n effective. I didn't get your question actually. N effective, it comes from beta. Beta is always K0 and effective. From there we got K0 and effective. And now in this step I have approximated that N1 is approximately equal to N effective. Both N1 and N effective it's eliminating, right? So I haven't not used N1 here. Is it confusing or what? So let me write in detail. So previously we have K0 square delta n square over 4 beta. Beta is K0 and effective. And this will come around 0.401. Now for delta n square, which is nothing but the sigma. Sigma is, okay, so please wait for 1 minute. My tab got disconnected. So delta n is like, I have to use the tab. Let me check doing. Okay. Now, okay. So now delta n square. So as I said before, so this is nothing but sigma. Sigma is the expression for sigma is 2 n1, which I said, or you can approximate n1 is. So you can take n effective as n1. So either you can write this is n1 delta n over 4 k0 n1 0.401. So n1 is cancelled, k0 is cancelled, 2 will cancel. So now we have k0 delta n and 2. Okay. So we have the expression k0 delta n over 2. multiplied by 0.40. And if you simplified it further by taking 2 pi over lambda for k0, so this will come around pi delta n over lambda 0. So is it clear now? Earlier you wrote an effective with the okay. Okay, then it's fine then. Okay, so what I was saying is this is the general expression for kappa, which is coupling coefficient. Uh, in addition to the term that we have seen before, we have a additional term which is the transverse overlap, which is I. Okay, so whenever the wave that is propagating, it's not a plane wave, then you need to calculate what is the value of I. But if it is a plane wave, we can take it as a I equal to 1 because it will come around, it will come as a 1. So that is why in question number 1, 2, or in the previous question, we have taken K is pi, K in terms of pi delta n over lambda 0 or lambda b. Okay, so let us move to question number 7 then. Question number 7 is easy. So I would suggest for you to calculate and let me know the answer. Okay, let me read out the question first. A fiber Bragg grating is designed to reflect light at a Bragg wavelength. Lambda b is 1550 nanometer. The grating period is also given. It is 530 nanometer. The fiber supports fundamental mode with an unknown effective index and effective, which satisfy the pure phase matching condition, which is this, that is gamma is 0 here. Then find out what is the effective index of the fiber mode. That is an effective. Calculate it and let me know the answer. 1.462. Yes, you are correct. This will come around 1.462. Okay, so let us see question number 8 then. So question number 8, it's based on a aperiodic fiber Bragg grating. That is the period, that is the grating period. It's not same along the fiber length. So depending on the position, the period is varying. Okay. So this aperiodic fiber, it is also known as chopped fiber grating, fiber Bragg grating. So in the question it is given a chopped fiber Bragg grating has a linearly varying grating period, which is given by this expression, where lambda 0 is 530 nanometer, alpha is given 0.02 nanometer per millimeter. Total grating length, it's also given, which is L 25 nanometer. So let me write what is given to us side by side. So grating period, it is varying along the propagation direction as lambda 0 plus alpha z, and lambda 0 it's given 530 nanometer plus alpha it is given 0.02 nanometer per millimeter. L is given 25 mm. Given that the reflected wavelength spans from lambda b minimum 1548 nanometer to lambda b maximum 1552 nanometer. So find out what is the effective index range that satisfy the pure phase matching condition. So we have a grating period line. So if we draw the figure, so as z increases, the period increases. So that means if we have this, so as we move, the period is gradually increasing like this. So that means at different position, different wavelength will be reflected back. And the maximum and minimum is already given. Now you need to find out what is the range of n effective. So I think if you just use the formula, you can get it. Because already all of the things is given to us. So let me do this for you. So let us see what is it said equal to 0. We have the grating period is lambda 0, which is 530 nanometer. So this is the minimum grating period we have, and the maximum will be at z equal to L, which is gamma L is not gamma, so it's like inverted V. So lambda 0 plus alpha L. Lambda 0 is 530 plus 0.02, and length it is given 25 millimeter. So this will come around 530.5 nanometer. So the maximum period will be 530.5 nanometer. Now, because according to the pure phase matching condition, we have gamma is 0, right? So gamma is 0 means lambda b satisfy the Bragg equation, which is an effective grating period. So for chopped fiber Bragg grating, we have lambda b, which is varying alongside. This is to an effective lambda z. So n effective will be lambda b z by 2 grating period. So to find out what is the maximum value of n, n effective maximum means the lambda b z should be maximum. 2 grating period, it should have a minimum value. And what is the maximum Bragg wavelength given to us? 1552 nanometer. 1552 nanometer. And minimum value of the grating period is lambda, sorry, 530 nanometer. So this will be 1.464. And similarly for minimum value, we have lambda b z should be minimum. This is only for to find out the range. Should be maximum. Lambda b minimum, it's given 5048 nanometer. To maximum is 530.5. So this will come around 1.459. Okay, so now we have the answer. And effective, it will lie in the range 1.459 to 1.464. Let us see question number 9. Okay, so let me give you to solve it. So this one is based on our previous concept. So if you recall the condition for what to find out what is the number of modes for a planar waveguide, then you can find out what is the answer for this. So it's a step index, not a fiber, it's a waveguide, planar waveguide, and it is given the refractive index of the it is N1 is given 1.51 and 2 is given 1.50 in air, and the core radius it is given 2 micrometer. Then the question asks find out the number of modes supported by such waveguide at lambda 0 is zero point 0.6 micrometer. So just find out what is the value of V, and if you remember the trick to find out what is the number of modes for planar, then you can get the answer. So this is the first part. We'll see what is the next part. First, find out this. So V is, I think you already know, this is 2 pi over lambda 0, a square root n1 square minus n2 square. So let me know the answer. So you just need to find out what are the total number of modes that is guided by the fiber. So what is the value of V you got? Six. A is 2. I1 square 1.5 square 0.630. Let me check. Um, no, it's not correct actually. Let me check again. So, no, it's like I think you have missed the term 3.63. Maybe a typo. So it will come around 3.63. 7.49. No, it will come around 3.63. So is it clear or I need to because all the things is given, so you just need to put it. So to find out the number of modes, what do we have to do? So instead of calculating the V in terms of by multiplying all the parameters, just separate the pi here. So pi and other terms will give a value of 0.578. Okay. And to calculate for planar waveguide, to calculate the number of modes, what we have to do? So we have to divide the V by pi by 2. So that is why I have taken pi here so that it will cancel with the denominator. Now we have V is pi 0.578 and pi 2. This will cancel. This will give a value of 1.156. So to find out what is the number of modes, if you recall, I suggested you to take a integer number which is closer to 1.156 but greater than it. So that means this will be 2. Okay. So the total number of modes will be 2. And if you recall, 2 means the fundamental mode will be guided, T is 0. And the next higher order mode, T1, it will be also guided inside the planar waveguide. So is it clear? If it is clear, then we will move to next part of it. Okay. So to find out the number of modes, what is this is the trick. Okay. It's like to one way is to look at the BV curve and to find out what is the V value where the in which range it is lying. So if you recall, we have a curve like this, right? And there is a spheric circle also. And this is pi by 2. This is pi. So depending on the value of V, you can look at what is the uh, V value and what are the number of modes that you can that can be supported by the fiber. The other way is like to find out what is the ratio of V by pi by 2. So you have to divide V, the V parameter you got, by pi by 2. So that is why I have expressed V in terms of pi. So I haven't multiplied pi with the whole parameter. So this V we got pi into 0.578 divided by pi by 2. So this will cancel and this will go here. So this is 1.156. Okay. Now we have a value 1.156. To find out it's not like the number of modes will be a fraction, right? So it will be a integer value. So that is why I've said to find out the number of modes, we need to look for a integer number, which is, let's say the integer number is n, which is closer to 1.156, but greater than it. So 1.156, it's lie between 2 and 1, right? It's lie between 2 and 1. So the integer which is closer to 1.156 is 2, which is greater than 1.156. So that is why to find out the number of modes, I have taken 2. Let us say we the V parameter maybe this integer came around 2 point or 12.8. So in that case, 12.8, it is lying between 13 to 12. So the integer number which is closer to 12.8 but greater than it is 13. So in that case, I will take 13. Okay. So is it clear now? So this is the trick that you have to, instead of if it is not given the graph. So that will be a hectic process. So, okay. So I haven't choose TE1 and TE2. So if you look at it is TE0 and TE1 because uh, when you have a, let's say we are, the fiber is supporting two modes. So that means TE0 mode, if you recall, this doesn't have any cutoff wavelength. So that mode will always be guided. So that means TE0, one mode will be TE0. So the next mode will be TE1 only. It's not like after TE0, TE4 more, the fourth mode of T is propagating. Because if you look at, it's like a solution to this. Okay, let us say if in the graph, the V is lying here. The V is lying here. This is the V value. Okay, okay, it's better in the graph, I think, instead of saying. So, okay, one thing, do I have I do have, I think it's in second tutorial. So the second tutorial, it's based on planar waveguide. So let me take this graph. So this is the exact graph. So if you look at V now, V is 0.578 pi. So that means it will be around. So let us say, okay, let us take an example, like, or V is 0.578. So this will lie here. Okay. So now if you look at the allowed solution in this graph, so allowed solution will be which points? The intersection point, like, right? So this is the solution to transcendental equation. Sorry. Okay. So these are the solution for transcendental equation. These are the curve. And this is the case where we are having circles like zeta square plus eta square is v square. So the allowed solution is like the intersection point, like here and here. So if V is in this range, so the two intersection point is this. One is T0, one is T1. Okay. So whenever two mode is propagating, one will be T0 and one will be T1. Next, if we increase the V, let us say we increase the V. So that means V, let's say V is now falling here in this range. Okay. So V is falling in this range. So if you see the intersection point, we have three modes. So this is one is T0, one will be T0, one will be T1, one will be T2. Okay. And to find out which one of the point correspond to T0, T1 and T2, what you have to do, you just remember the concept like the propagation constant of T0 is always greater than T1, then it is greater than T2. So beta 1 is greater than beta 2 is greater than, or beta 0, beta 1, beta 2. So from that, you can relate it to the V parameter. And from that, you can V or zeta you can also relate it to, and to find out what is the location of T0, T1 and T2. Okay, so let us see the last question. Um, okay, after the first part, so it was given that the refractive index of the two, let's say the fiber is now supporting T0 and T1, right? So let's say it is already given that the effective index of T0 is 1.50862 and effective index of T1 is 1.5046. Then what should be the grating period of the fiber Bragg grating for efficient coupling between these modes? So the fiber is now supporting two modes. One is T0, the fiber Bragg rating actually, T0 and T1. So how you can calculate what is the value of N effective? So in process, you have to use the transcendental equation, that is for T0, zeta, it's a even mode. So we can use zeta, tan zeta is eta. And for T1, it's a odd mode. So you can use zeta, cot zeta is minus zeta. So by solving this transcendental equation, you can find out what is N effective. But in our problem, it's already given N effective it's T0, it's already given 1.50862 and N effective T1, it's given 1.5046. Okay. So for efficient coupling, what we need that the phase mismatch, it should be zero. That means gamma, it should be zero. So gamma is nothing but beta 1 minus beta 2 minus kappa. It should be zero. Or kappa is beta 1 minus beta 2. Or you can write it as beta 0 for T0 or beta 1 for T1. And N effective is given, so we need to simplify it further. So kappa is nothing but 2 pi over grating period. And beta 0 is, it is, let's say this is delta beta, right? So we need to find out what is grating period, which is 2 pi over delta beta. So delta beta is nothing but, you can take it K0 delta n effective. K0 is 2 pi over lambda 0 delta n effective. So now we have gamma, which is lambda 0 delta n effective. So just put it here in this equation. So we'll get, you can express the grating period as lambda 0 over delta n effective. And lambda 0, it was already given in the question, it is 0.6 micrometer. And delta n effective is 1.50862 minus 1.5046. This will come around 149.3 micrometer. Okay, this will be the answer. So is this question clear to you? Because I think time is almost over. We'll stop it here. If you have any doubt, let me know now. Okay. So do you have any other doubt that you want to clarify? Otherwise, we'll end this live session and we'll solve the remaining part in the next tutorial. Okay, if not, let us end the live section. Thank you for joining the live section. I hope whatever I have solved, it will be helpful to you to solve the assignment problem that is floated weekly in the NPTEL site. So let us meet on next Monday, same time from 6 to 8. Okay, so thank you very much. Let us meet on next Monday. So bye everyone.